In this video, I will discuss about full adder circuit. Here we will discuss how to construct a full adder circuit. In my previous video, already we have studied how to implement half adder circuit, and also we know that half adder is a circuit which adds two binary numbers. For example, suppose 1 is added with say 0 1. We know that in half adder this 1 will be added with 1. It will generate the sum as 0 and it produces carry as 1. So as we know, in half adder it adds only 2 bits, but here we have 3 bits, 1 0 and 1. So to add 3 bits we must prefer using full adder circuit. So now I can say that full adder is a circuit which adds 3 binary bits. Half adder will add only 2 binary bits, whereas full adder will add 3 binary bits, so that the previous carry can also be added. Let me draw the block diagram of this. So that is, we have a full adder. Say it is full adder. It has 3 inputs. Let me take A and B as input, and we have another input, say C in, that is carry input. So here this one is nothing but carry input. Carry input is generated by adding the previous bits. It produces two outputs, say sum and carry. So for sum I will use the variable sum, and for carry I will use the variable carry out. So to implement the full adder, first we have to write the truth table. So here we have 3 inputs and 2 outputs. Here these 3 are inputs and sum and carry are the outputs. So now I supposed to write the truth table for this. Here we have 3 inputs and 2 outputs. So let A, B, C in are the inputs, sum and C out are the output. So we have 3 bits. The possible inputs are 2 power 3, that is 8. Let me write 0 to 7. 0 0 0. We have 0 0 1. We have 0 1 0, that is 2. 0 1 1, that is 3. 1 0 0 is 4. 1 0 1 is 5. 1 1 0 is 6. 1 1 1 is 7. So here I can write the decimal numbers, that is 0 1 2 3 4 5 6 and 7. Now we'll write the sum and Cout expression. When 0 is added with 0 and 0 is added with 0, it produces sum as 0 and carry out as 0. Similarly, when 0 is added with 0, it produces sum as 0 and carry as 0. When 0 is added with 1, sum will be 1 and carry will be 0. Similarly, here also we have 0 1 0. It produces sum as 1 and carry out as 0. So here 0 1 1. Let me add 0 and 1. That is, when 0 is added with 1, it produces sum as 1, carry as 0. So this 1 will be added. So 1 plus 1, it produces sum as 0 and carry as 1. So the result will be 1 0. That is, 0 is sum, 1 is carry. So it produces 0, sum as 0 and carry as 1. Similarly, 1 0 0 produces sum as 1, carry 0. 1 0 1, again it is same. We have 2 ones. So it will produces sum as 0 and carry as 1. 1 1 0, again produces sum as 0, carry as 1. 1 1 1, that is, when 1 and 1 will be added, we'll get 1 plus 1 is 0. It produces carry as 1. And when we add this 1 to the sum, it produces again sum as 1. So here sum as 1 and carry as 1. So this is the truth table for a full adder. Now let me write the Boolean expression. I will simplify this using K-map. So here we supposed to use 3 variable K-map. So this is the 3 variable K-map. So first I will try to get the expression, Boolean expression for sum. So let me write for sum. So these are the cell numbers. We have 0, 1. We supposed to write here 2, 3, 4, 5, 6 and 7. So here we have 3 variables. Let me use the variable A here, B and C in here. So B and C in possible inputs are 0 0, 0 1. So in K map we supposed to write 1 0 here and 1 1. So A can be 0 or it can be 1. So now we have to get the Boolean expression for sum. We supposed to see in output column where there exists 1. So here we have 1, which is the decimal representation is 1. So in cell number 1 we have to write 1. So here we have 1, that is min term is 2. So in cell number 2 we have to write 1. Then here we have 1. In min term here is 4. So cell number 4 we have to write 1. So here we have 1, that is cell number 7. So in rest all cases, in all cells we have to write 0. So let me do the grouping of ones now. So in this K map, 3 variable K map, it is not possible to do any pair. So all the ones are independent. This is 1. The expression for this is A, B bar, C in bar. That is, let me write some expression. Sum is equal to, we have A, B bar, C in bar, B bar, C in bar, plus here we have 1. So it is correspond to 0. 0 means A bar. We have A bar, B bar, C in, B bar, C in, plus here we have 1. It corresponds to A, B, C in. That is A, B, C in, plus here we have 1. It corresponds to A bar, B, C in bar. A bar, B, C in bar. So this is the sum expression of full adder. So this is the sum expression of full adder. The same thing I have written here. Now let me write the carry equation. So I can write for carry or cout. Carry means cout. So here the variables are A, B and C in. It is 0 0, 0 1, 1 0, 1 1. Here we have 0 and 1. Cell numbers are 0, 1, 2, 3. It is 4, 5, 6 and 7. So here for carry we have 3, 5, 6, 7. So in 3, 5, 6, 7 write 1, 3, 5, 6, 7. In other cells we are supposed to write zeros. Let me simplify this K map. So here we can make a pair with these two one. The value of this will be, here it is A. So it covers 2 columns. Here the common term is 1, which is with respect to C in. A, C in. And here we have 1 1. Let me cover these two. So this and this can be covered. The value of this is, again it is A, and here with respect to these two column, common term is B, which is AB. So now we have one more one here. That one and this one can together, I can make a pair here. So here the value of this will be, we have it is with respect to column B, C in. We have B, C in, and here there is no common term, so it is B, C in. Therefore I can write the carry out expression of cout as, cout is equal to, we have AB plus we have B, C in, B, C in, plus we have A, C in. So this is carry out expression of full adder. So now we found the Boolean expression for sum and carry. The next step is we have to implement using basic gates. So before proceed for implementation, we'll try to simplify this sum expression further. Let me simplify this further as, in this term and this term there is A is common. I can write it as sum is equal to A. I will take A as common. This will be B bar, C in bar, plus here we have B, C in, B, C in, plus similarly now comparing these two terms, this one and this one. Here I can take a bar as common. I can write a bar. So the remaining terms are, it is b bar Cin plus here we have b Cin bar. B Cin bar. So I will try to simplify this further. That is sum is equal to A. We know that b bar Cin bar plus b Cin is nothing but b x nor Cin. This is nothing but b x nor Cin plus here we have a bar. So here it is b bar Cin plus b Cin bar is nothing but XOR. XOR between b and Cin input. That is b Cin. So now let me consider, let b XOR Cin is equal to Z. So therefore now I can represent this equation as, that is sum is equal to, I can write A. So here it is b XOR Cin is nothing but Z. Here we have complement of Z. That is Z bar plus here we have a bar. So b XOR Cin is nothing but Z. So now further I can write as sum is equal to, so this is nothing but a Z bar plus a bar Z. That is nothing but a XOR Z, or I can write some expression as sum is equal to a XOR Z is nothing but b XOR Cin. That is b XOR Cin. So this is the simplified expression of sum in full adder. That is a XOR b XOR Cin. That is, for the given input, just take the XOR between these three inputs, we'll get the sum expression. Now let me implement this. Sum is equal to a XOR b XOR Cin, and for C out the expression is AB plus B Cin plus Cin into A. So let me implement sum. So for A XOR B XOR C, here we can use 3 input XOR gate, or we can also implement using 2 input. So take 2 input XOR gate. The first input is say A and another input is say B. So output of this is, we have A XOR B. So now output of this goes to another XOR gate. Let me use another XOR gate. So here A XOR B is the input, another input is C. Say that is C. So output of this is nothing but sum. That is A XOR B XOR Cin. Let me take it as Cin. So this is the sum expression. Now let me implement C out. So to implement AB, we need one AND gate. Here we need one AND gate. Here we need one AND gate. Let me use 3 AND gate here. So one, we have second AND gate and we have third AND gate. So for the first AND gate, the inputs are A and B. Say this is A and we have B. The output of this is AB, and we have B Cin. So here we have B and we have Cin. So output of this is B Cin. So for another AND gate, the inputs are Cin and A. So we have, this is Cin, and let me take A. So this is A. The output is Cin and A. So there is a plus between these product terms. It means we have to use OR gate to combine all this. Let me use OR gate. So output of this is nothing but C out, or carry output, or carry. So this is the implementation using XOR gate and AND gate and OR gate. This is the complete structure of full adder. Now let me implement the same full adder using 2 half adders. So in this circuit we have used the basic gates. Now I will try to express or try to implement the full adder using 2 half adders. That is full adder using 2 half adders. let me consider the same truth table which already we have written. So this is the truth table, and also we know that the sum expression we got is A XOR B XOR C. So now instead of using the simplified Cout expression, directly I will write Cout expression from this truth table. That is, we have Cout is equal to, so consider the row where there is 1. So here we have 1. The corresponding inputs are A is 0, B is 1 and C is 1. It can be represented as A bar, B, C in. If there is 0, we have to take complement of variable. If it is 1, we have to take direct variable. And here we have 1, which is A, B bar, C in, plus A, B bar, C in, plus here we have A, B, C in bar, A, B, C in bar, plus here we have A, B, C in. That is A, B, C in. So here I can take C in as common. C in. So here it will be A bar B, plus here it will be A B bar, plus in these two terms I'll take AB common, that is AB. This can be represented as C in bar plus C in. So this is nothing but we have C in. So A bar B plus AB bar is nothing but A XOR B, plus here I can write it as AB. C in plus C in bar is nothing but 1. So therefore the modified carry expression is, we have C in A XOR B plus AB. So now we will use this carry expression and this sum expression to implement this using two half adders. So as we know, in half adder, already we have studied the half adder. Half adder circuit consists of one AND gate and one XOR gate. So here let me implement sum expression, that is we have sum as A XOR B XOR C in. So let me take one XOR gate. So inputs are, one is A input, say this is B, A and B. The output of this is A XOR B. Let me take one more XOR gate here. So output of this is connected to this XOR. Another input is, say, C in. Here the output is sum, which is equal to A XOR B XOR C in. C out is equal to C in A XOR B. So here we have A XOR B. So I'll take one AND gate. It is nothing but A XOR B dot C in, means we supposed to use AND gate between C in and A XOR B. So one input to the AND gate is A XOR B. This is A XOR B. Another input is C in. This is one thing. Plus we have AB. So AB. So I'll use one AND gate here. The input to this is, one is A and another one is B. Now output of this and output of this will be added. That will be done using OR gate. That is, let me take one OR gate here. So input to OR gate is, one is output of this, which is nothing but A XOR B C in, and another output here it is AB, that is connected here. So output of this is nothing but C out, which is equal to A XOR B C in plus we have AB. So here we can observe that in this circuit, so these two is nothing but one half adder circuit. So this is one half adder circuit. I will call it as HA1, and here together this one and this one forms another half adder. So this is another half adder 2. So thus we have implemented the full adder using two half adders. So let me draw the block diagram of this here. So we have HA1. HA1, for HA1 inputs are, one input is A, another input is B. The output, so some output of this is connected to another half adder. Let me draw another half adder here. So this is HA2. This is some output is connected here. This is some. So its carry output, and here it produces the final carry, final sum, that is sum, and its carry and this carry together given to OR gate. So output of this is Cout. So this is block diagram representation of full adder using two half adders. Now I will try to implement this sum and carry expression using only NAND gates. So this is the sum expression, that is A XOR B XOR Cin, and Cout is, as we know, it is Cin multiplied with A XOR B plus AB. So in my one of the video, so just refer this video where I have shown how to implement XOR gate using NAND gates. So here we know that A XOR B, and there is a XOR operation with Cin. So let me implement A XOR B. So with this implementation we need only 4 NAND gates. You just refer this video to understand this A XOR B using NAND gates. So here take one NAND gate like this. One NAND gate is to be connected here. One more NAND gate is to be used here, and here we have one NAND gate. So here for the first NAND gate, let the input is A and B, that is A, this is B. This A input is connected to one of the input of this NAND gate, and B is connected to one of the input of this NAND gate. The output of first NAND gate is connected here, and it is also connected here. The output of this is connected here, and output of this is connected here. The output of this will be A XOR B. So now here A XOR B is implemented, XOR Cin. So this is the input to the next gate. So this A XOR B is in turn XOR with Cin. So now another this kind of structure will come. For that, one of the input is A XOR B and another input is Cin. So A XOR B acts like A input and Cin acts like B input. Let me draw the same circuit, this kind of circuit once again. That is, here we have one NAND gate like this one. Here we have one NAND gate. Here we have one NAND gate, and here we have one NAND gate. So output of this is connected here, output of this is connected here, this output is connected here, this output is connected here. This is one of the input for the NAND gate. Another input is, here we have Cin, and output, this is connected here, this is connected here. So output of this is nothing but A XOR B XOR C, which is equal to sum. So this sum is implemented using only NAND gates. Now we'll try to implement carry out, which is equal to Cin A XOR B plus AB. So here I can simplify this as, we have Cout is equal to Cin A XOR B plus we have AB. I'll take complement on both sides so that I can get Cout complement is equal to, we have Cin A XOR B plus AB complement. Let me simplify this. I'll apply De Morgan's theorem here. That is Cin A XOR B bar dot we have AB bar. So therefore here I can write, again I will take complement, taking complement again, this will become complement of complement is Cout, that is same variable. Here I can write Cin A XOR B complement dot AB bar, and we have to take one more complement. So this is the final expression. Now I will try to implement this. We can observe that C in A XOR B, C in is one of the input, A XOR B whole bar, that is nothing but, here we can get, look at this circuit, here we have A XOR B and C in, the output here is nothing but this entire term, and another input is AB bar. So as we know, here the output is AB bar, so I'll use one more NAND gate. One of the input for this is from here, that is nothing but this entire term, and another input is AB bar, that AB bar is available here, I'll take from here and it is connected to here. So the output of this will be carry, which is nothing but this entire output, that is nothing but C out. You can call it as carry or C out. So this is how we can implement even using only NAND gates. Thank you for watching.